Hey, good afternoon or morning, maybe even evening, depending on when you're watching. Today is day two in our related rates min-max unit. We're still doing min and max work, and today we're going to look at cost and volume and surface area examples. So I have three examples that we're going to work through today. Tomorrow will be a work period containing work from max and minning from yesterday and today. So today will be probably about that 35, maybe a little longer minute video. And then tomorrow will be a full work period. I think I have a sheet with some solutions here. I just worked out the solutions. Yeah, I've got a sheet of about 10 or 11 problems to work through. Don't have to do them all, but some of them that you'll work on tomorrow. But today I want to focus on, we did area, maxing and min type problems yesterday. A couple different examples of that. Maybe I think we did three. Here we're going to do three examples again. So this first one that we're going to do is cost. And you can get that down in a minute here, and I'll flip ahead here. We're going to do one of constructing a box that maximizes volume. And then we're going to do one of building a box and knowing what the volume is that you need, and then minimizing the surface area of the box or the material that you need. So let's start off with this one here. It says a rectangular field is enclosed with a fence. On one side, the field is against a wall so that no fence is required on that side. If the material for the fence costs $3.50 per meter for the two ends and $4.50 per meter for the side that is against the wall, find the dimensions of the field with the largest area that can be enclosed for $1,200. So let's work this one out. So this is like our area ones that we were doing, except we are going to use the cost equation to get instead of the perimeter, to get one variable in terms of the other, and then we're going to maximize or minimize in this case, maximize in this case the area of the field. So we're actually not minimizing cost in the example here. This is the wrong way to put it. We're actually maximizing area for a particular cost is what we're actually doing. For a given cost. That's actually what we're doing. We're not minimizing the cost. That's something else. It's very similar, but it's something else. Okay, so let's go ahead and do this example here together. Let me just clean up some area here. There we go, and get my writing pad here. Okay, so if I were to, and I'll go with, let's see here, let's go with green today. Okay, and then, all right, so we've got the wall here, and we've got our two sides coming out like this, and we're going to say that we'll have some width and then some length here. Okay, so we have to get the cost and use the cost instead of perimeter, because it doesn't tell us how much fence we have. It tells us how much money we have. It's telling us what it is per meter for this. So if we do this side, it's $3.50 per meter at the two ends. So this would be $3.50 W, and this would be $3.50 W, and that would be the cost where W is how many meters it is. And this one here is actually $4.50 L. So our cost then equals $3.50 W plus $3.50 W plus $4.50 L. So if I were to add that all up and equal it to $1,200 for our cost, the cost equation would be $1,200 is equal to $3.50 plus $3.50 is W plus 450 L. So there's our cost of building the fence depending on what the dimensions of W and L are. So we want to maximize the area. So our area equation then is still length times width. So I'm going to solve for L in this case, or you could solve for W, and then we're going to plug it into here. I'm going to solve for L in this example. So we're going to say L, 4.5 L. So we're going to subtract 7W from both sides equals 1,200 subtract 7Ws. Okay, we got to take our calculator out and divide out 4.5. So L equals, okay, what's 1,200 divided by 4.5? 1,200 divided by 4.5. That gives us 266 2/3. Okay, so we got a little bit of rounding going on here. So it's going to give us a little bit of inaccuracy. So we'll just go 266 point, you could use fractions if you wanted. We'll say 67 minus 7 divided by 4.5. What is that? Okay, it's 1 5/9, which is 14 over 9, or 1.55555. So we can say that this is 1.56 W's. Okay, we are going to just use decimals in this case. We could go ahead and use fractions to get exact values, but we're going to be okay if we do decimals because it's going to be, we're talking about hundreds of a meter, like centimeters, so we'll be fine. So this is our equation of length. So we're going to have to plug this into for the area equation here. So we're going to take this and plug it in. Then we'll have area in terms of W only. So the area then is going to be just W times this that we have here, 266.67 minus 1.56 W's. So when we do that, okay, we end up with the area being equal to 266.67 W minus 1.56 W squared. Okay, now we want to maximize the area for that cost. So in order to get maximizing of the area, we have to take a critical number or find a critical point. So that means derivative. So we take the derivative and set it to 0. So A prime is what we're going to do, and that's going to be a 0. So A prime, so this is going to be 266.67. Okay, W drops out, minus 1.56 times 2, which would be 3 point, what is that going to be? 3.12, I think. Just better double do it here. Yes, sir, 3.12 W's. Okay, that's our derivative. And if we equal it to 0, we now solve for W. So this A prime is 0, so we can move this 3.12. Let's put those decimals in there so that we don't get mixed up here. Okay, so this 3.12 can be moved over to the other side here. So that becomes 3.12 W equals 266.67. Now we're going to divide each of these sides by 3.12 to get what W is. So we go 266.67 divided by 3.12. Okay, and we've got 85.47, which we'll say 85.5. meters. Okay, that tells us what our value for the width is. What about this length here? Well, our length equation is right here, which we can just plug it in. L equals 266.67 minus 1.56 times 85.5 meters. Okay, so with our calculator, we take our 85.5 times 1.56. Okay, that's 133.38, and we subtract that from 266.67, and we get 133.3 approximately. So this would be 133.3 meters. So our dimensions are 85.5 meters for the width side coming out of the wall, and the length would be 133.3 meters. If we wanted to figure out what the area is in square meters now for the $1,200, we go 133.3 times 85.5, and we get 11,397 or so square meters. So 11,397 square meters to the nearest meter I'm doing there. So I'm rounding it off. So, and if you think about that cost, okay, if you wanted to double check your answers, you could go, okay, well, is that going to give us $1,200? Let's double check it. You could go, okay, so I have 133 meters. So 133.3 times 450, right? Plus 85.5 times 2, because there's two widths, times the cost of 350. And you should get, I didn't get exactly $1,200, but you should get $1,200. Okay, so you could double check your answers a little bit to see how you get. So there's our first example, a cost example. Okay, and in the practice assignment, we have a couple of those for you to do. Let's go on to our next example here. Okay, let's see what I answered here. It says, find the dimensions of the field of the large area. So the dimensions are here. I put the area down as well, but I kind of answered two questions there. Okay, our second example, if I flip ahead here, is constructing a box out of, like when you make those Christmas boxes. So it's a volume maximization question, really. So it says, a box is to be made from a piece of cardboard by cutting a square from each corner. Now, sometimes I say a rectangle or whatever, but a square from each corner. If the cardboard is 48 centimeters long by 27 centimeters wide, find the dimensions of the square to be cut out to maximize the volume of the constructed box. So if we look at the diagram here, I've got the piece of cardboard. Here's what we're going to cut out. So let's define that as X by X. It's a square, so each side has to be equal. Okay, and there's our cutting pieces that we're going to cut out. And it tells us that the length of this piece of cardboard is 48 centimeters this way and 27 this way. Okay, so we're actually going to have, this is going to, if we fold this up, this piece here is going to be like the width of the box. If we fold this up, these X's are going to be the height of the box, and this piece is going to be the length of the box. So we have, this is our length, this is our width, if we fold it up, and this is going to be our height. X is going to be our height. So our volume is equal to length times width times height, and we have to write each, what is the length? Well, the length here, it's going to be 48 minus an X there and an x there, so that's 2 x's. The width here is going to be 27 minus an x here and an x there. That's 2 x's, pardon me. Right, there's an x there and an x there. So it's 2 x's. Okay? And the height is just going to be, if we fold this up, it's going to be a height of x. Okay, so let's write out the volume now that we know all the dimensions. So the volume equals the length, which is 48 minus 2x. Okay? The width, which is 27 minus 2x. And the height, which is just x. Okay, so we have it all in the variable of x. So we have one variable, so we don't have to convert anything. We just have to expand it so that we can maximize this volume of this box. So we're going to get our calculator out to do some multiplying of 48 and 27 here. Okay, so that's 1296. So the volume equals 1296. Okay, and then we get 48 times negative 2, which is negative 96x. And then we got negative 54x. And we have positive 4x squared, all multiplied by x, and then we expand it out. So the volume equals 1,296x. And we're going to combine these two to get minus 150 x cubed, or no, x squared, what am I saying? Because this is x and x times an x, it's only x squared. X squared. And then finally plus 4x cubed. Okay, so there is our volume equation in terms of x. Okay, we can rearrange it into a cubic equation with the x's, but we're going to take the derivative to find a critical point. So we're going to find v prime, and we're going to set that to 0. And this is going to be equal to 1296 minus 350x plus 12x squared. Okay, now quadratic equation is coming up here. So let's write this as 0 equals 12x squared minus 300x plus 1296. And you're like, holy smokes, that's really hard to factor. Well, it might be factorable. I doubt it because I just made this one up. Let's see if 12 goes into 1296 evenly, and then 300. Okay, 12 goes into 300 25 times, and 108 times into the other one. So we can factor this. Minus 25x plus 108. Now, I don't know if it's plausible here and then we can get rid of this 12 because we divide by 12 on both sides. So 0 is going to be equal to x squared minus 25x plus 108. So we're going to have two negative factors that multiply it to 108. Well, 12 and 9, but 12 and 9 are not going to add up to 25. So it's going to be some decimal number. So the only way to solve this, we can't factor it evenly. We could go to Desmos and plug it in and find the x-intercepts, or we could just use the quadratic equation. Minus b plus or minus b squared minus 4ac over 2a is equal to our x. Okay, one's going to be a negative and one's going to be a positive value, or one's going to be one that doesn't fit in there maybe. We'll see. Okay, so negative b, so that's 25 plus or minus square root of 25 negative squared minus 4 times a, which was 1 in our case, and c, which is 108, over 2 times 1. So 25 plus or minus. Okay, so let's go with the squaring 25. Negative 25, that's 625. Okay, and then we're going to subtract 4 times 108. Okay, that's a negative 432. And if we add to 625, we get the root of 198.3 up here over 2. So take the root of 193 on our calculator. That is approximately 13.9. So our answer is equal to x. So x equals 25, sorry about the chat there, plus or minus 13.9 over 2. So 13.9 plus 25 divided by 2 equals 19.45, or say 19.5. Or let's do the other one. 25 minus 13.9 divided by 2 equals 5.55 or 5.6. Which one makes sense? Well, this is 27, so if this thing was 27 wide, so if we're cutting out 19.5 and 19.5, that's not going to fit there. So that one makes no sense. So the one that makes sense is 5.6. So therefore, we can say that the square is 5.6 centimeters by 5.6 centimeters. Now, I'm going to check my chat here. As you saw, I had a couple chats there. So I'm just going to pause for a second, and I'll finish this off when I get back. Okay, so as we can see, there's our dimensions. So now, what did it ask us? It says to maximize, find the dimensions of the square to cut to maximize the volume. So if I ask you for the volume, you could figure out, we've got the square, but the dimensions are the height equals 5.6, the length. Okay, so if we did the length, if we go back up to the top here, the length was 48 minus 2 times 5.6. And the width was 27 minus 2 times 5.6. So if we do that, 5.6 times 2 is 11.2. So if we subtract that from 48, it's 36.8. And this one here, if we take 11.2, and oops, sorry about that, their calculator, 27 minus 11.2, we get 15.8. Okay, so there is our cut. Square is 5.6 by 5.6. Our dimensions are 5.6 high, 36.8 long, and 15.8 wide. And we can multiply all three together if we needed to find the volume as well to get our max volume. Okay, let me just get this chat thing out of here because it keeps doing that. There, and then we can focus on what we're doing here. Okay, so that's our second question. Let me take a look at where am I here with the time. Okay, so that we're about 25 minutes. So we are going to go fairly long today. Sorry, guys, because I still have this one to go through yet. So be about 30 some minutes for sure. It's going to take us about 10 minutes to do this one. Okay, so this is using surface area and volume. So sometimes you get the surface area and you have to maximize or minimize the volume. Sometimes you get the volume, like this case, and you have to maximize the surface area. So it says a box has a square base, no top, and 4 congruent rectangular sides. So our square base, like that. I can't really, I'm going to draw this with straight line tool because it's hard to draw in here with this marker thing. All right, so let's go to the straight line tool. Okay, so we have okay, there's our thing, and we'll label it up a bit. So there is no top. Okay, and let's say it's a square, so that's each of these dimensions x and x. Okay, so the square dimensions are x and x. And let's call the height of the box y. Okay, x and x and y. Okay, defining those areas. So that it tells us the volume. So the volume is equal to x times y. Okay, so that's our first equation. And we're minimizing surface area, right? So it says, what is the minimum total area of the base and the sides, and what are the dimensions corresponding to this minimum area? So we're minimizing the surface area. So we're using the volume equation to get rid of one of the x or the y. And it's probably easiest to write it in terms of x because we got two x's and one y. So we can say that the volume, which is 124 cubic centimeters, equals x squared y. So if we solve for y equals 124 x divided by x squared. Okay, we're going to divide x squared. Okay, so that's how we figure out the y. So that's what that is. So now the surface area, it's going to be equal to 4 sides and 1 base. There's no top. If there's a top, you'd have 1 base and 1 top. That would be two squares. So the 4 sides, the sides are x times y, and the base is x times x. So if we write the surface area equation now, it's going to be 4 times x and y plus 1 base, which is 1x squared. Now, if you had a top, it would be 2x squared, but you don't have a top. It's missing the top. So now what we're going to do, sorry, itchy shoulder there, we have to minimize this surface area. It says area, but it's really surface area. So to minimize it, we're going to take the derivative and equal it to 0 of this particular, this particular question. But we have a y here. So what we have to do is we have to plug this y in here. So maybe I'm jumping the gun a little bit. First, we have to, before I can take the derivative, I don't want to use implicit differentiation here if I don't have to. So I'm going to use a substitution then to get rid of this y before I take the derivative. Pardon me there. So the surface area then is going to equal 4x times the y, which was 124 over x squared, plus our x squared here. So let's multiply the 4 and 124 times 4. That gives us 496. So our surface area equals 496, okay, x over x squared, so one of the x's cancels out on the bottom, plus x squared. Now we have it all in terms of x. So we're going to rewrite this in terms of an exponential form so that we can use the power rule for our derivative. So we can say that the surface area then equals 496 x to the negative 1 plus x squared. Now I can set this to 0 by taking the derivative of the surface area and setting it to 0. So this is going to be equal to, if we take the derivative, it's negative 496 and the x to the negative 2 plus 2x. Okay, now this is set to 0, so this is 0. So we're going to remove this to the other side. So we've got 496. X to the negative 2 we can write as x squared like this on the bottom, equaling 2x. Okay, then we can cross multiply. We can say 2x cubed equals 496, because this is 2x over 1. So 496 times 1. So divide by 2 to get that 2 out of there. You get x cubed is equal to 248. Okay. All right, so now we have to do cube root to get our x. So cube root, oops, got to push 3 first. And then my cube root of 248, okay, equaling 6.28 or 6.3. So 6.3 for x. And what we're using centimeters. Okay, now we need to find out what y is. It's up here. Y would be equal to 124 divided by 6.3 squared. What is that? 124 divided by 6.3 squared. I get 3.12 or 3.1. So our dimensions are 6.3 by 6.3 by 3.1. So we've got 6.3 by 6.3 by 3.1. So it's actually a shorter box to maximize the area. And then that would be a volume of whatever that would be, 6.3 123 square centimeters. Okay, so what are the dimensions corresponding to this minimum area? Oh, if we wanted, actually, we know what the volume is. It's supposed to be 124, right? So we were off by a little bit of rounding. Sorry, we're supposed to put surface area down here. My mistake. We already know what the volume was, right? It's asking us what is the surface area. Okay, so we have to go to the surface area equation, not that one. So we know the dimensions, which we have here, but we're going to plug it into this surface area. Sorry. So 4 x, y plus 2x, or sorry, plus x squared. So this would be 4 times x, 6.3 times 3.1 plus 6.3 squared. There we go. So we'll work that out. Sorry about that. 4 times 6.3 times 3.1 equals 78 point something time plus 6.3 squared. So 117.8 square centimeters. Is our surface area. Okay, so there's our surface area. And our dimensions we wrote out before, 6.3 times 6.3 times 3.1. That's our dimensions. Okay, so there's our 3 examples of doing those types of problems. Now, next day I'm going to give you a work period that deals with doing examples from day 1 and 2 of maximizing and minimizing volume, area, surface area, cost, and things like that. So I did 6 examples. They're very similar to the examples that are coming up in the practice assignment. You don't have to do them all, but you'll be working on that tomorrow. Okay, so maybe I'll do a quick little introductory video to say, here they are. There's 11 of them. Do these ones, or at least some of them. Okay, so good luck on that tomorrow, and we'll see you next day.